with this stuff to make things maybe a little bit more efficient, a little bit easier. The first thing is to understand that when we deal with any object that we propel upward, okay, we're going to go straight up right now, is going to follow the quadratic equation h of t. Mark where it works. So you go h of t is equal to negative 16 t squared plus initial velocity times t plus then an initial height. Okay. Sometimes you'll see, like a textbook call this, instead of h they use an s, and over here instead of an h they use an s. Just for s, for a lot of times it refers to position instead of height. We're going to use h as much as we can. And then negative 16 comes from the acceleration due to gravity. The differential equation that we're dealing with is actually negative 1/2 times g times t squared plus initial velocity plus initial height, where g is gravitational or acceleration due to gravity. And in feet, that's 32 feet per second per second. So half of that is 16, and we multiply it by a negative. Where that comes from, you don't need to worry about it. I explained a little bit in the video yesterday about where it comes from. But you need about 2-3 calculus courses underneath your belt to really understand why we can have that formula. And that's kind of the thing about mathematics. Sometimes we're high school students, college students, high school students right now. Maybe in our first college math course or one of our last high school math courses. And we're doing things using formulas that we really won't learn why and how to use them and why they exist until 4 or 5 classes from now. Does that make sense? And that's the thing about math sometimes, is that you can learn to do some stuff with the formulas, but sometimes the formulas you got to take for granted, and that's one that right now we're taking for granted. For the most part, I'm pretty sure that your textbook in WebAssign is always going to do things in feet per second. If for any reason they ever do it in meters per second, this will be a negative 4.9 t squared plus v sub naught t plus h sub naught. So this one's feet per second, this one's meters and per second. Okay. So that's going to be useful if they ever change the units on you. Try to keep with the 1 in feet. And I put feet per second or meter per second because that's kind of how you're going to know when they tell you the velocity. They say the velocity is 80 feet per second, so now I'm using negative 16. If it said velocity is 80 meters per second, then I use the negative 4.91. Okay? But everything else is the same. The way you approach these is identical, regardless of the units you're dealing with. This question here, so we'll get into the question. So the ball is thrown directly upward from an initial height of 100 feet with an initial velocity of 80 feet per second. So if you were thinking about this, and I showed this again with GeoGebra yesterday, if you're thinking about this situation, it's going straight up, this ball is going straight up and coming straight down. Does that make sense? And that's that's in the situation that this is our x and this is our y in regards to displacement of that object, or that ball in this case, from the origin. Okay? If you think about like throwing a baseball or kicking a soccer ball or something like that, normally that object, you're going to think about it taking kind of that course, right? Taking a parabolic course. And that makes sense. If I kick the ball from here, okay, in a two-dimensional plane, that is going to be the course. That's how far, and I get to right there, that point right there, is how far the ball is away from where I started or where I kicked it in an x direction, and how far it is away from where I kicked the ball on the ground in a y direction, right? Okay? But that's called horizontal and vertical displacement. And that's really not what we're doing right now, because our axis right now is a time axis, okay? And our y-axis is a height, an h of t, okay? And we're thinking about our ball going straight up and straight back down. So we don't see necessarily in an x and a y, we don't see displacement left or right. Does that make sense? It's going straight up the y-axis, coming straight back down if we left them as x's and y's. But when we replace the x-axis with the t-axis of time, now we're saying when this ball goes straight up and comes back down, against time, it's going to do something like that. Okay? Those are going to be the data points that we recognize. Okay? Now, in the particular problem they have here, they're saying that the initial velocity is 80 feet per second. So we just throw in that v sub naught, that variable is 80, put our t on. And our initial height, okay, they say we're going to do this from 100 feet. Okay? So in the event of graphing this correctly, what would be my y-intercept? What is the, if t is 0 time, what is the height of my ball? 100, right? Okay. So we're at maybe 100 right there. And I'm going to throw this ball straight up, and it's going to come straight back down all the way to the ground. Okay, so it's going to go below where I'm standing when I throw it. Does that make sense? Okay. But if I gauge this against time, my curve is going to do something like that. Okay. Hopefully it looks maybe a little bit more parabolic than that. Okay. Now we're interested in finding some certain things about this. Okay, we can ask a lot of different questions about this, but one thing that they're going to ask is, okay, if we got a point right here where like time is 4.8 and we get this number there. Okay, they're going to ask you, what does that ordered pair mean? Okay, well, to us, every ordered pair on this curve is a t comma h of t. Okay? Usually we like to use x and y, right? That's more, I think, visual for people. It's more simplistic to look at as x and y. But these are our axes of t and h of t. So every first coordinate is a time. Okay? So we got at 4.8 seconds right now. Does that make sense? Okay? And that then is the height evaluated at that time. So when I take 4.8 and I plug it back into this, maybe I get 115.36 back. Does that make sense? So it tells me at a time of 4.8, my ball is at that height off the ground. Okay? And that's very important that we understand that, and we can use that information now to learn other things about our graph. Okay? One of the first things I want to talk about, when we didn't talk about yesterday, we didn't talk about how we can find this value every single time, is the vertex, the highest point on this curve. Okay, so that point right there. Okay, when you find your vertex is always located at the opposite of b over 2a. Okay, so going back to my quadratic equation, take my b term, make it negative, and divide by 2 times my a term. And then the y value, okay, if this is ultimately my time, then my height, which we sometimes say is our y value, right? That's the way we kind of think about things. If this is my time, I should be able to take that time value, plug it in here, and spit out a height, right? Okay? So I'm going to write h evaluated opposite b over 2a. And that's how you find the ordered pair for your vertex of any parabola. Okay? It doesn't necessarily have to be this modeling situation. Okay? Any parabola that we ever want to deal with, take opposite of b over 2a, and that becomes your x coordinate, or in this case our t coordinate, and then you plug that back into your function, and that gives you your y coordinate, or in this case your h of t coordinate. Okay? So now, doing that for this problem, the opposite of b, so negative 80 over 2a, so negative 32. All right, and that is going to evaluate to, I believe, 2.5. Okay, usually I don't like dealing with decimals like that. Usually I like leaving it like 5 halves or whatever, but it does come out real nice at 2.5. Now what we're going to do, if that's the time in which we reach our maximum, I can now plug that t back into this function. So take negative 16 times 2.5 squared plus 80 times 2.5 plus 100. Okay? Plugging that back in should give you that to be 200. Okay, and I think I've got that. I'll show that on my calculator here. So negative 16, 2.5 squared, 80 times 2.5 times, or plus 100, then it does give you that 200. And that's just evaluating that thing. Okay. There are some other ways, some easier ways maybe to evaluate that. If I were to take this function and type it into my calculator, type it into y1, okay? So I've already gotten y1, okay? The next thing I'm going to do is I'm going to go to second table set, okay? Second table set, which is, that's actually the window button. And we're going to go down now to the independent variable. You guys know which variable is the independent one? In science, what is the one thing that you guys cannot change or alter or anything like that? What never stops, whenever time, right? Time is independent of everything, right? Your x variable, or in this case, your t variable, because it's time, is independent, okay? And what we're really doing here, when we hit second table, what I'm really doing here is we're going to create a t-chart, right? When you guys were in Algebra 1, you created a t-chart, you chose x values, right? And then you plug those in to get y values back, right? Well, you chose any x values you want. So that is independent of anything else. Whatever you want to choose, okay? Those numbers did not rely on anything else. But if I chose, for this case, 2.5, does my y value or h of t value now depend on that 2.5? Yeah. So the number that you choose is independent. That's the x value or the t value. And then the y value is the dependent variable. Okay? So I'm going to just type in 2.5 right here. And it evaluates that function for me real quick. That makes sense? Might be a little bit easier than doing it by hand. There are other ways of doing it. If I go second quit, I think if you go to so you just saw I went to vars, V-A-R-S, go over to y-vars, and then click function, and then I've got my function listed in y1. So if I hit y1, it's going to do that. And I'm going to put a parenthesis, 2.5, and then hit enter, and it should give me the same 200 back. I just think that technique is a little bit more of a pain in the butt to find all those hidden functions, but it does work. There's a variety of different ways to find that. There's nothing wrong with this, but using that table is a little bit easier if they want me to evaluate a 2.5 and then 3.5 and then 4.5 and then 6.5, stuff like that. Does that make sense? You want to do multiple evaluations pretty quickly. So that tells me that the height of this thing, the greatest value in regards to the y value or the h t value that ball gets to is 200 feet. Is that doable? Okay. And again, that's using that vertex concept. Okay. The next thing they want to know are questions like when and what time interval will this object reach 160 feet? Okay. So in what time interval will the ball be greater than 160 feet? Okay. I think this is one of the harder questions because of the algebra that we have to do after we create the equation. Okay. So really what we're interested in is that we're at 100. You know, 150 maybe is right there, so maybe 160 is right there. Okay. We want to know if I draw in that horizontal line of y equals 160 or h of t equals 160. Doesn't that line intersect my curve at two spots? Make sense? We know the y value right now of those two spots, don't we? Isn't the y value of that spot 160? Isn't the y value of this spot right here 160? Okay. Now we're trying to find the t value that's associated with this. Okay. Well, remember that's an h of t value, right? So can I say that that number, h of t, is now 160, set equal now to my quadratic equation that will solve then for t? Is that doable? Okay. So I'm going to take that quadratic equation. It's getting kind of messy here, but we got I want to solve this for t, so the way I'm going to do that is use the quadratic equation. That's the easiest thing. These numbers are really nasty. They usually don't factor real cute in an easy manner. So quadratic formula is usually what you just want to start with anyways. So I'm going to go 0 equals negative 16t squared plus 80t, and then what? Minus 60? Is that okay? Now how do I solve for t here? Using my quadratic formula. Opposite of b, negative 80, plus or minus b squared. So what's 8 squared? 64. What's 10 squared? 100. So 64 times 100, 6400, right? Okay. Minus then 4 times a times c, all over 2a, which would be negative 32. Okay. Now doing that, we can again grab our calculator. Negative 80. I want to go plus first. Square root 6400 minus 4. Now when you do this way, make sure you put in your parentheses to do the multiplication. It just saves you from making errors. And that's the numerator. I'll divide the numerator by negative 32, right? So one time value is we'll just say 0.919. Okay, 0.919. So that would be that t value right there. That makes sense, everybody? I'm going to plug that ordered pair in. 0.919, 160 is now the time, h of t that we're at 160. The next thing we have to do is find the other time value. Well, we've already done all the work, so use your calculator to help you efficiently. I've already typed all this stuff in, and really the only thing that needs to change is that plus becomes a minus, right? So hit second, enter on your calculator as many times as you need to recall that last line, or the line that you want. Okay? Your calculator will store 10 previous lines for you that you've typed in. Does that make sense? Have you seen that before? Okay. In this calculator you're using on your computer, you might be able to set it in the options to store like maybe 50 lines or 100 lines or something like that. I'm not sure. Now I'm just going to go back in, edit, change that to a minus, hit enter, and now divide that number by negative 32. So that's my 2a on the bottom. And I get 4.08. So the other time is 4.08. Is that number right there, which visually is 4.08. Is that all right? Okay. So that's not necessarily answering the question yet, because it says in what time interval will the ball be greater than 160? Okay. Now with our rough rounding here, we now have exactly the values of when it is at 160, right? Well, at 160 is not greater than 160, right? So we want to go from 0.919 up to 4.08. Okay. Now with rounding and all that kind of stuff, you could probably argue maybe some of this notation, but I'm going to make sure that I don't include those two values because they wanted the interval where we're greater than 160. Now the idea is then, well, since I rounded that number up, I could actually include that number. Does that make sense? Okay. This, I don't know, we rounded that one down, I think. So you would exclude that one. Okay, but I'm not going to really argue that. Let's put just open parentheses there. Is anything greater than 0.919 and less than 4.08 will definitely be greater than 160. Does that make sense? Let's show how we can get that on our calculator. When does this thing hit the ground again? Okay, and we've already done something like this. I think those two questions are harder. Okay, finding the vertex and finding when it's at 160. The next thing is they're going to say, when does this thing return to the ground? When they say return to the ground, they're implying what your y value should be. Okay, what y value should I have, or h of t value should I have when I hit the ground? 0. Okay, so they're saying instead of this being 160, it's now 0. Okay, And now we just do the quadratic formula again. Opposite of b plus or minus b squared minus 4 times a times c now at 100 all over negative 32. That'll be my time. Okay. Now, one of those time values that they give you back, I'm going to just, for the sake of time here, I'm going to go to the next slide and see if they actually do this. Okay. When we go through and do this, we should get 6.04 for one of these t values. And that makes sense, right? But look at my graph over there. Where does the other t value, where does this other side of our parabola, where does it cross the t-axis? What type of numbers over there? Negative. Okay. So you get a negative time, which mathematically is fine because the numbers in the equation doesn't really know that I'm dealing with time, right? It doesn't really know that, hey, he only wants the positive answers back. Okay. So you have to distinguish positive answers from negative answers when we're talking about time. Okay. So the only time this thing comes back to 0 is at that 6.04, which is one of those quantities when you evaluate that. Okay. The other one's going to be a negative something. Okay. And the other one is going to be just kind of thinking about this. If this is that time is 6.04, and the vertex was at 2.5, okay, we should be able to do subtraction there, find out what that difference is. 6.04 minus 2.5, it gives me 3.54. Does that make sense? So the distance, what I just found, is that distance right there between the axis of symmetry for a parabola and one of the x-intercepts. And it's that distance that is green is 3.54. So can I take and subtract from this number 3.54 and find that other x-intercept over there? Okay. So when I take 2.5 minus 3.54, these two time values, without even evaluating this, I now know that these two time values were 6.04 and negative 1.04. That one we don't count because it's a negative time, right? Okay. That's kind of how we deal with those types of functions, those types of real-life situations with some algebra. And this is stuff that you might do this in physics when you guys shoot off your rockets. Okay, at some point you'll make rockets, and maybe, I don't know, maybe Mr. C used to make rockets with his class. I don't know if you guys do that lab still. But they would calculate this stuff. Okay. Anybody that goes into the military and works with ballistics or anything understands this math. Okay. And it understands. We're just skimming the surface, but they do a whole lot more with this stuff. Because we would like to be able to shoot down a ballistic from North Korea at some point, right? Okay. So it'd be nice to make sure that those people that are doing this stuff understand this physics and understand this math to be able to do that. What I want to show you guys is how to use your calculator to do this. Okay, because you're seeing here that that's a lot of what's going on in the PowerPoint. What I want you guys to do, get your calculators out, and you're just going to go to y equals. Throughout the year, one of the goals that I have is for you to become a little bit more efficient with your calculator. Not necessarily let your calculator do the work for you, but to maybe enhance your work, to provide some insight to you that maybe you didn't have prior to using your calculator. So in y1, all I want you to do is type in negative 16. Now we don't have t's here, so we're going to use x, which is fine. Squared plus 80x plus then 100. Okay? Now if we graph this, and most of your graphs are going to be initially standard view, which they start you from like negative 10 to positive 10 on the y-axis and negative 10 to positive 10 on the x-axis. Okay? Obviously that doesn't get much of our picture in there, right? So we got to go mess with the window. Alright, so I need you guys to click on the window key. Okay. Now we've already done some of the work here, and sometimes when you use your calculator, maybe you haven't already done all the preliminary handwork, like we've done on the whiteboard. So sometimes finding your window and finding a good window might be kind of trial and error, where you adjust the numbers, you go back to the graph, and you get the whole graph in, yes or no. If it's no, go back to the window, readjust, remanipulate the numbers, and then see. Does that kind of make sense? So it's back and forth sometimes. But we've already done a lot of this, so let's say the x minimum. I'm really not interested and anything to the left of the x-axis, or sorry, the y-axis, right? So let's just make our x minimum either 0 or maybe, I don't know, -1 or -2 or something like that. Our x maximum now, what was our vertex's height at? Or sorry, what was the vertex's, not the vertex, the x-intercept, what was its largest value? Say it again. Careful, I misspoke. What's these values? What's the largest x value that we had? It was this one, right? 6.04? Okay. So let's make our x maximum a little bit bigger than that. I'm just going to go to 8. Okay. X scale, all the scale means is this is how many kind of markings you're going to see on your axes. So you'll see 9 markings if we leave that at 1, right? I can change it to 2 and say it's going to put a mark every 2, and so forth. I think I can leave that at 1. Now my y minimum, okay? My y minimum I don't care about. It's not going to be negative. All right, y values, I'm not interested in negative y values, right? But what we want to make sure is that when we go through our calculator, you see this stuff over here, these numbers. We don't want those numbers to show up on top of our x-axis, so we've got to push our x-axis up a little bit. So I'm going to say my y minimum, I'm going to leave it at -10 and see if that works. Okay? But my y maximum, what was the maximum of the vertex? What was that height? 200. So I've got to change this to a pretty large number. I'm going to go to 220. Okay? But now my y scale is 1. So what it's saying is that between -10 and 220, I need a mark for every integer between those. That's kind of unrealistic, isn't it? Okay? So let's say that we put, let's just go by 20s. Okay? And now we'll graph it. And that looks somewhat realistic, doesn't it? Okay? Now understand what this means. Because of the scales that we use. That's 0, that marking is 1, that marking is 2, that marking is 3, 4, 5, 6. Now on the y-axis, they're not going by 1s, right? We chose to go by 20. So 20, 40, 60, 80, 100, which is mimicking then that place that we stood on the y-axis and threw that ball. Okay? The next thing we would want to do, if I want to see when this thing, I'll finish this video and do the calculator portion during third period today. About fell down. And put that on the website so you know how to use your calculator for the homework. Okay? Just finished